Hi everyone, today we are going to be discussing our lab, determining our equilibrium constant with spectrophotometry. This lab has a lot of pieces to it that have to come together in order to get our final result. So the way that I'm going to structure this video is I'm kind of going to lecture and then do our lab and then move on to our next piece of lecture and then do our lab and then go into more of our calculations portion, just so we can take one step at a time, just like you will in your lab itself. Now, if you're doing the lab virtually, I will say that the experimental portion in LabFlow is not as built up as our previous labs, so there's no data that you are going to be recording. Instead, what's going to happen is LabFlow is going to say, do you want some provisional data? And you're going to say, yes, I do. It'll say, are you sure? And you're going to say, yes, I do, because Dr. Burns gave me permission to do that. And you're going to essentially be given fake data that was already pre-recorded for you. So what I'm going to show in this first part of the video is how that data was obtained and what it actually means. So in the first part of the lab, or I guess in the lab overall, we'll talk about that first, we are looking at the equilibrium reaction between iron 3 ions, thiocyanate, which is SCN, thiocyanate, in equilibrium with iron thiocyanate ion. Okay, so since we know our equilibrium equation or reaction, we can find our KEQ, and this is going to come in handy for the second part of our lab, because essentially what we are going to be doing is determining our equilibrium constant from these different concentrations at different points in equilibrium. We're essentially going to be shifting our equilibrium left and right in our reaction depending on our concentrations. And what we should see is that K is going to stay constant, because as we've discussed in our Le Chatelier Principles lab, K is going to stay constant when we change the concentration. It's just going to shift our equilibrium one way or another, but the concentrations are going to change to account for that. Okay? K can only change when we change our temperature, which is what we saw in our entropy of borax lab, where we took equilibrium calculations for each different temperature. So this one, we are now exploring how to find K when we change our concentration. And essentially what we're going to do is find 5 different values of K, average them together to get an overall K for this reaction. Okay, so how are we going to do that? Well, it's not as easy as just mixing some solutions together and finding those concentrations, because we can't really find those. As we know, as you've talked about in class, in order to find equilibrium concentrations, we're going to do some ice tables. So the second half of our lab is going to be ice tables in order to find those concentrations. But before we get there, the first thing that we have to do is take a skill that we learned back in Gen Chem 1, which is dilutions. Okay? So we are going to take multiple different solutions of varying concentrations of iron thiocyanate and iron thiocyanate. We're going to dilute them to different concentrations. And what we're going to do is create a standard curve in order to find a linear relationship between our concentrations and the number that we can get out for it, which is called our absorptivity or our absorption, okay, from the spectrophotometry portion of our lab. So let's talk about that. In order to create our standard curve, the first thing we have to do is make our standard solutions using dilution. They're standard solutions because we know their concentrations with a lot of confidence. And as we'll see, we'll use a lot of really volumetric-based glassware in order to find those definite concentrations. So as you may remember from Gen Chem 1, a dilution uses the equation M1V1 equals M2V2, where M stands for the molarity or the concentration, and V stands for the volume. And we're looking at how the molarity changes depending on the volume change, okay? So in our lab, the first thing that we did, which you are unfortunately not going to be able to do, but you're going to see me do, is we're going to make 5 standard solutions. And those standard solutions are made up of the iron ion, the thiocyanate ion, and some extra nitric acid, which is just there to fill the rest of our volume up. It is not participating in this reaction at all. It's just what all of these solutions are dissolved in, okay? So essentially what we're doing is we're taking the iron ion and mixing it with the thiocyanate ion. And as we can see in our handout that we get from LabFlow, the iron concentration is staying the same, or the iron volume is staying the same, which suggests that we're keeping its concentration the same. But we can see that the thiocyanate concentration right over here in the middle is what's changing. We're going from 0 milliliters to 1 to 2 to 3 to 4 and to 5 milliliters of that thiocyanate. And essentially what that's going to do, as I increase the concentration of my thiocyanate, it's going to shift my equilibrium to create more of that thiocyanate. Okay, that's Le Chatelier's principle. If I increase my concentration of one of my reactants, the equilibrium is going to shift towards my products. So we're going to start making more of this product. As we make more of that product, we are going to increase its concentration. Okay, so what we should see as I add more and more of this, these solutions are colored, so as we get a higher and higher concentration of our iron thiocyanate, which is a really nice red color, we'll see that it gets redder and redder with every dilution that we make, because we're increasing its concentration every time we increase the concentration of the thiocyanate ion. Okay, so from LabFlow we have this table of our volume of iron, volume of thiocyanate, and volume of nitric acid. Okay, and what you need to do in the calculations portion of the lab is determine the final concentration of that thiocyanate ion. Okay, so how do we do that? Well, we know M1. M1 is going to be the solution of potassium thiocyanate. That's what the thiocyanate ion is dissolved with, is potassium, or sodium, sorry. I believe on LabFlow it may also say potassium, it just kind of depends. They're the same thing, they're in the same group, they're just there as a counter ion, so don't worry if it's different, okay? All we care about from that information is the concentration that we get. So in my concentration that I'm going to be using in our lab today, that concentration is 1.00 times 10 to the minus 3 molar. Your concentration is going to be different because, as we know, we all get different values in our LabFlow labs. So just make sure you are using the correct value that LabFlow gives you for that concentration. It'll just be listed. It'll say the concentration of sodium thiocyanate, or in some cases it may say potassium thiocyanate. Again, those are interchangeable. As long as they have a concentration next to them, we can use them. So it'll say the concentration is this, okay? It might be different than what I give here, okay? So we know our concentration of our thiocyanate. That's going to be constant through every dilution that we're going to do in this first part, okay? The volume, V1, is then going to be the volume of the thiocyanate that we add to that test tube. And as we saw from our table, that is what's going to be changing. Okay, it's going to go from 1 to 2 to 3 to 4 to 5. Okay, so that's going to be varied. So I only have one example up here where I have 10 milliliters of the iron and 1 milliliter of the thiocyanate. Okay, so we'll do an example with the 1 milliliter, then you'll go on to do the 2, the 3, the 4, and the 5 milliliter independently. Okay, so that's our M1 and our V1. M2 is what we're looking for. That's what we're solving for in this dilution. That will be the final concentration of the thiocyanate ion in our test tube, okay, after we've done our dilutions with the iron and the nitric acid. That'll be our final concentration there. And then V2 is the overall volume that our test tube is getting to. That is also going to be constant for every test tube in this portion of the lab. We know what that final volume is because in our chart, and as I have shown here, the HNO3, or the nitric acid column, says to dilute to 25 milliliters. So these volumes are going to vary, okay, because of the different amounts of the iron and the thiocyanate that we're adding, okay? But we're always going to dilute to 25 milliliters, meaning that in part 1, our final volume for our test tube is always going to be 25 milliliters. Okay, so for part 1, we know that our final volume is going to be 25 milliliters. Again, our M1 is also going to be constant. I have this concentration, yours may be different on lab flow, so make sure you're checking that. The volume of the thiocyanate is going to be given from that table, so you'll know what it is from the table in lab flow, okay? And then the final concentration, the M2, is what we are looking for. So now that we have 3 variables of our 4 variable math problem, we can solve for M2. So how am I going to do this? Well, I'm just going to set up my dilution. I'm going to do 1.0 times 10 to the minus 3 times my volume of my thiocyanate, which in this case, for the example I'm showing here, is 1 milliliter. I'm going to keep that in 1 milliliter because the final volume is also known in milliliters. Those units will end up canceling, so I don't need to convert them. All I want is my final molarity in molar, which this initial concentration is already in. So the units work out for us that we don't need to convert anything here. Okay, so I'm going to multiply that by 1 milliliter. And that's going to be equal to M2, which is unknown. I ran out of room, so it's a linear kind of thing. I just ran out of room here. M2 times our final volume of 25 milliliters. Okay, so we just solve for M2. I believe I have this here. So M2 is going to be equal to 4.0 times 10 to the minus 5 molar. 5. Okay, again, your concentration, your final concentration may come out different than mine because your initial concentration that lab flow gives you may be different. Okay, so if you're not getting this exact number, that's okay. As long as you're plugging in the numbers in the same way that I am, noting that this concentration is going to be different, okay, then you will be good to go to get your M2. Okay, so that's how we solve M2 for test tube. I think this was test tube number 1. What you're going to do now is solve for test tube number 2, 3, 4, and 5. The only thing that's going to vary in that calculation is this concentration, right? The concentration, whatever it is that is given to you, the initial concentration is going to stay the same, okay? That's not changing, it's just coming from a bottle, okay? In lab flow, it's coming from a bottle, that's standard. Then our final volume is always going to be 25 milliliters, as we see from the table in our handout, that it's always going to be diluted to 25 milliliters. The only thing that's varied in these different test tubes is the volume of the SCN. So the only thing that's going to change is this volume 1. So it's going to change with each test tube. So when you go on to do test tube number 2, it'll then be whatever concentration times 2 milliliters is equal to M2 times 25 milliliters. So none of these other numbers will change except for this initial volume. Then obviously M2 will change because of that. Okay, so that's the first part of part 1, is just making these solutions and finding those concentrations using our dilution, which I'll show you how we do here in a second. What we then do with that information is going to be used to set up our standard curve. Now, if you took General Chemistry 1 with me previously, you learned about Beer's law and a Beer's law plot. And that's what we are doing here, where essentially we are going to take these different solutions that are slightly different colors, and we are going to put them into a spectrophotometer, okay? And what that spectrophotometer does is it measures how much of a specific wavelength of light is absorbed by that solution. As a solution gets more and more concentrated or darker in color, it's going to absorb more and more light, okay? So our absorbance should increase as our concentration increases, okay? And this is a direct linear relationship. So if we know the concentration and we can find the absorbance experimentally, which is what we are about to do, we can take those two values and we can compare them in a linear plot in order to use that to find future relationships between absorbance and concentration, okay? So once we mix these two solutions together in our test tube, we are going to get a nice red solution, like a burnt orange kind of red solution. that red solution is the iron thiocyanate ion, okay? And that's what we are measuring the absorbance of. So we did this reaction with differing concentrations of iron and thiocyanate, and we are going to then mix them together and create different final concentrations of iron thiocyanate. So that red color, as we'll see in the experimental portion, will get darker and darker and darker, because as I increase my concentration of thiocyanate, I'm increasing my concentration of iron thiocyanate based off of Le Chatelier's principle. Add more reactant to create more product, okay? So what we would end up seeing in our data is that with each test tube, as I increase that concentration, we're gonna see an increase in our absorbance. So what we are going to plot in Excel, okay, is the relationship between the concentration and the absorbance value. The concentration here is what we find from our dilution. So I know that test tube 1 has a concentration of 4.0 times 10 to the minus 5. And what we are going to find in the experimental portion of this lab, and what LabFlow gives you virtually, is the absorbance value. So right here I have it as a just as an ampersand, as a number sign, okay? I don't know what it is yet. That's what we'll find in the experimental portion. And we'll do that again for test tube number 2, number 3, number 4, and number 5. Again, those are the concentrations that we can calculate using our dilution here. And then we'll find the absorbances in our experimental portion, or if you're doing the lab virtually, LabFlow will give you those values. Okay, so we're gonna plot concentration versus absorbance. Concentration is gonna go on the x-axis, and absorbance is gonna go on the y. And what we're gonna see is a linear positive relationship between these two values. So once we have this direct linear relationship, which I kind of have an example shown here, you're gonna have a bunch of different dots, making sure to include a blank of 0, 0, because as our concentration is 0, our absorbance should be 0. Okay, you'll have a plot that gives a linear relationship. So you're gonna do a linear regression and find a y equals mx plus b equation, which we've done in multiple labs so far. So we'll take that y equals mx plus b, and that's the piece that we need to use in our second part of the lab, which we'll explore later. Essentially what this is showing us is how the absorbance and the concentration are related. Now, so as we see, y is our absorbance value, that's our y-axis. X is our concentration value, that's our x-axis there. This m, the slope of that line, is something called the absorptivity, or the molar absorptivity. This is going to be a constant for every type of reaction. Okay, you can look up absorptivities for different reactions online, or you can find them experimentally because they're not always perfect. Okay, so we are experimentally determining our molar absorptivity. This is kind of the relationship factor between the absorbance and between the concentration. It's how those relate based off of this specific reaction. And this is why we can't just take a dilution, find an absorbance, or find those concentrations and use them directly, because based off of the absorbance that we find, or the difference in the color, okay, we have to relate them using this value, okay? So this is a constant, and that's what we'll just use for our next portion. What we're gonna find in the second part of the lab is, well, if I know an absorbance value, and I know the rest of my y equals mx plus b, I know m, I know b, I can use that absorbance value to solve for concentration. And that concentration is the equilibrium concentration of the iron thiocyanate. That's how we're able to find the equilibrium concentration of iron thiocyanate, which we can then use in our ICE tables, right? Because in ICE table, we need to know information about the initial concentrations, and we need to know information about the equilibrium concentrations in order to find K. For finding K, we need both initial and equilibrium concentration information. This y equals mx plus b plot is what is going to allow us to find that equilibrium concentration relationship, and our dilution is what we can then use to find our initial concentrations. The dilution math-wise is the same in our second part, but we do have some slightly different values to use. Okay, so we'll take a look at that when we get to part 2. What I want to jump into now is the experimental portion that relates to part 1. So what you're going to see me do is the dilution of my first 5 test tubes. You're then going to see me use our spectrophotometer, and we'll see how the absorbance changes with each of these different concentrations, and then we'll plot our concentration or our calibration curve, our standard curve, and we'll be able to find our y equals mx plus b plot and our equation, so we can then use that for the second part of the lab. Okay, so this is the part where we are doing our dilutions in order to make our standard solutions. So I have in front of me my plot or my table that has the different volumes that I need to use to make these solutions. I have my my sodium thiocyanate, my iron nitrate, and my nitric acid that I'm going to use to dilute. Now, I'm going to make each of these solutions in a volumetric flask. Now, these flasks are made to be exactly a specific volume. So I don't know if you can see it, but there's a little line, my black glove will help show it off. There's a little line that when I raise my solution up to that line, I know that it is exactly 25 milliliters. So essentially what I'm going to do is put my different volumes of each solution into this volumetric flask. I'm then going to dilute it with my nitric acid all the way up to that line, mix it up in order to make my solution. Now, in order to get my volumes of my thiocyanate and my iron correct, I'm going to use a volumetric pipette. This is similar to our volumetric flask where there's a line on the pipette, and when I bring my solution up to that line, I know that I have exactly 1 milliliter of that solution. The reason we want to use these rather than something like a graduated cylinder is because the volumes are so small. It's really hard to tell if I get my meniscus exactly at 1 milliliter in a 10 milliliter graduated cylinder. So these are just easier, plus the delivery method is really simple. So what I'm going to do is use my pump here. So this essentially is what's going to suck up the liquid, and I'm going to add my specific volumes of each of these into my 6 volumetric flasks. So I'm going to start with my iron nitrate because that's my constant volume in each of these. So this is 5 milliliters, a 5 milliliter volumetric pipette. I'm going to do this twice into this first one. What I'm going to do, I guess what I'm going to do here is I'm going to do our first test tube. So I'll do the blank in the first test tube, so blank in number 1, and then I'll time lapse me doing 2 through 5, just because it's the same process, it's just different volumes, so there's no reason to sit here and watch me do that for 20 minutes. So in order to make the blank, my chart says that I need to have 10 milliliters of iron nitrate, 0 milliliters of the sodium thiocyanate, and then I'm diluting the rest of the way with my nitric acid. So I'm not using any thiocyanate. The reason this is called a blank is because it's basically the solutions that when we go into the spectrometer, we want to cancel out. These are solutions, we can see that the iron nitrate is orange, and as I said in our pre-lab lecture, our final solution is going to be red. Basically what this is going to do is tell the spectrometer, cancel out all of this wavelength of color and only focus on the other wavelength of color that I want. Okay, so this is what we consider a blank solution. So what I'm going to do is put my pipette in here, and I'm just going to pump it up till I get 5 milliliters, and I'm going to transfer that to my flask. Kind of hard to do by myself. Sometimes it's nice to have the partner do it. And then I'm just going to push this down to make sure I get all my liquid out. So that was 5 milliliters. And now I'm going to do another 5 so that I get 10 milliliters total. Okay, and I'll just push this down to get all my excess solution out. And I'm done with my iron nitrate portion. Since the blank has none of the thiocyanate in there, what I'm gonna do is then use my nitric acid to pour into my flask in order to dilute it the rest of the way. Now with a volumetric flask, once I get to kind of the neck portion of it, it fills up pretty quickly. So what I'm gonna do is fill the rest of the way up with my nitric acid, probably right until I get to the neck of my volumetric flask, and then I'm gonna use a pipette to do the rest of the way so I get my meniscus perfectly at that line. Okay, so now I'm just gonna take my pipette, I'm gonna get on eye level. There we go. So in my flask right now, I have exactly 25 milliliters of my blank solution. I'm then just gonna put a cap on it, flip it upside down a couple of times so that it mixes together. And that's my first solution of my blank. Next, we are going to do test tube number 1, which, as we saw from the beginning of our pre-lab lecture, is going to be 10 milliliters of the iron nitrate, 1 milliliter of the sodium thiocyanate, and then we will fill the rest of the way with the nitric acid. So I'm gonna follow a similar routine or procedure where I'm gonna do my 10 milliliters of my iron nitrate. So I'll do this twice. So that's 5 milliliters. Another 5 milliliters, so that's my 10 milliliters of my iron nitrate. Now I'm going to add my 1 milliliter of my thiocyanate. I'm going to take my 1 milliliter pipette and do the exact same thing. And what we're going to see is a slight reaction. So now you can see how my solution got a little bit darker. So it went from that yellow color of the iron nitrate to now a more orange color. That's the start of that red solution that the iron thiocyanate is starting to make. This is our lowest concentration solution out of the entire list. So as I get lower and lower, it's gonna get darker and darker, okay? So what my last step to this is going to be filling the rest of the way with my nitric acid. So we'll do that here. And I'm going to use my pipette to fill the rest of the way. Oops. Okay, we can cap this. And we can flip this upside down in order to mix it. Okay, so those are my first two solutions, my blank and test tube number 1. Now I'm gonna move these to a test tube just after I've made all of my solutions so that it makes sense that I'm calling them test tube number 1 and 2 and everything like that. Okay, so what I'm now going to do is I'm just gonna time lapse my next 4 test tubes. Again, it's the same process. The only thing I'm varying is my volume of the thiocyanate solution, okay, just like my table tells me. So as you'll see, these solutions will start to get darker and darker. So here are my 5 solutions plus my blank. Might be a little hard to see in the camera, but they are getting darker and darker in terms of how more red they are comparing to the blank. Maybe that comparison is kind of easier to see. But as you saw when I was creating it, they also got darker and darker. So now that we have our standard solutions and we can now calculate their concentrations, the next thing that we need to find is the absorbance. How much light do each of these solutions absorb now that my concentrations are varied at specific amounts that I now know? So what we're going to do for that is use this thing called a spectrophotometer, also known as a colorimeter. Colorimeter meaning a meter that can count colors, figure out colors, okay, track colors, okay? It's literally a color meter. And what I can do is I can set this to a bunch of different wavelengths that maybe different solutions will absorb, and I can measure how much that solution absorbs of that specific light. As we said before, as I increase my concentration, it's going to absorb more and more light, because the darker the solution gets, the more light it's going to absorb or not let pass through it. So I'm going to set this. We're going to set this up and start our readings for our different absorbances. So my colorimeter here is wireless, so I have to connect it to an app on my phone or my iPad in order to measure the absorbance. So that's what's shown on my iPad here. The absorbance is being read right here. Right now it's being read as 0.02. Now ideally when it's closed and only my solution is in there, or no solution is in there, we should read it as 0. But as we discussed before, I have a solution that we refer to as a blank. And what we were saying was, because this iron nitrate solution has a color to it, and the iron thiocyanate solution has a slightly different color to it, what I'm going to do is blank out my colorimeter here, my spectrophotometer, and basically say, ignore this color and only focus on the other color. So what I'm going to do that is I'm going to take this, which is a cuvette. It's just a smaller little container that I can use to put directly into my colorimeter, and I'm going to put my some of my blank in there. And then going to cap off my cuvette to make sure I don't spill any of it, and I'm going to put it right into my colorimeter, and I'm going to hit the calibrate button. Now, as we can see, the absorbance is starting to go up and down. What it's basically saying is I'm passing some light through this solution, and I'm saying, okay, I'm absorbing this much. I'm now going to subtract that off and say, I don't need this. It's almost like when we're on a balance and we want to tear out or cancel out the mass of, say, the weigh boat or weigh paper that we're putting our solid on. So now we can see that now that the calibration's done, that my absorbance is reading as 0. It's basically saying that this color is now zeroed out, and I no longer, or the colorimeter is no longer going to read it. So what I'm going to do next is take each of my test tubes here, and I'm going to pour it into the cuvette, put that cuvette into the colorimeter, and record its absorbance. So here's test tube 1, which is our lightest solution, so it should be the lowest in absorbance. we can start to see that my absorbance is going up a little bit. Sometimes it takes a little bit just to read through, but it's about 0.0607. Okay, so now what we can do is then do the next solution. So now I'm going to do test tube number 2. So here's test tube number 2. So we should see that absorbance go up a little bit more. And there it goes. 0.14, 0.15, kind of through there. Now these are the values that LabFlow is providing to you. So that's the provisional data that it was asking about. It essentially gave you these absorbances. So you can see that there was a lot that went along the way to get those numbers, and that's why I wanted to make this portion of the video to show exactly where they're coming from. So we just continue on. Now that we did test tube 2, we're going to do test tube number 3. We're going to close that and let our absorbance read. So we can see that now at test tube 3, my absorbance is going up even more, 0.23. It was just at 0.15, and we'll continue doing that. So we have 2 more test tubes to do this. Goes again. Now it's that much higher, 0.30. And we'll go into our last test tube. And there we go. So we see that our absorbances are going up and up and up with each solution. If you are completing this lab in person, just like I am, and actually have these solutions in front of you, and say 2 of your solutions have very similar absorbances, that may be a little clue for you that something went wrong, and maybe one of your solutions was not at the proper concentration. So this is a really great way to look at, as you go through the lab, if all of your solutions were made properly. So now what we're going to jump to next is taking these absorbances and plugging them into our Excel plot in order to make our standard curve. Okay everyone, so let's look at our data from this first part of the lab. So in my Excel sheet, I have everything plugged in. So for each test tube, I have its concentration that I've calculated using my M1 V1 equals M2 V2 dilution equation. I showed you how to get test tube number 1 for my specific numbers during our pre-lab lecture. And then I went and calculated the other 4 independently. Now, just keep in mind, these will not be the exact same as your numbers because your concentrations will differ from mine. Okay, so you can't just copy these numbers as is, they will differ. Okay, so I have my concentrations here, and then I went through my video of our lab experiment, and these were the absorbances that I recorded for each of those test tubes. Okay, these are the numbers that you are given in your lab flow. So they automatically give you these absorbances. They may not give you this blank, okay, but make sure you include it. So when the concentration of our iron thiocyanate is 0, the absorbance would theoretically be 0 as well. Okay, so we need to have this blank in here as well. If it's not shown in our lab flow, we need to include it there as well. So now that I have concentration and absorbance values, what I can do in order to make my standard curve or my Beer's law plot, whatever you call it, Okay, we're going to highlight the concentration in the absorbance columns. I'm not going to highlight any of the words. You can see that I don't have any letters besides my times 10 to the E here. I'm not showing any molarities or anything like that because that does throw off the curve or the plotting in Excel. Okay, so no units or anything in these columns. So now that I have them highlighted, I can go to my insert, and I'm going to go to my little scatter plot option here, XY scatter. Okay, I know this may look slightly different if you're using Excel versus Google Sheets, but ideally they're in similar spots. They are set up the same way, but you want to choose a scatter plot. Now, I personally like a scatter plot without the line, so it's easier for me to see the y equals mx plus b line, so I just choose this scatter plot here. And automatically it gives me my plot. Now, let me zoom in a little bit. We can see that our absorbance values are here on the y-axis, and we can see that our concentration values are here on the x-axis. So what you'll do when you are doing this is you will then go in and label these axes. Okay, but we can just compare our numbers from our two columns to where they are on either side. If for some reason you don't have this positive looking plot, your axes are most likely swapped from each other. Okay, so just keep that in mind. We need to have absorbance in the y and concentration in the x. So now what I'm going to do is I'm going to click on my plot. I'm going to right click on any of these, if it'll let me. Maybe. There we go. Nope. Come on. Why we no click? There we go. Right click on that. There we go. And then we're going to add trend line. I'm pretty sure there's a way that we can do that in this upper portion here. I just choose to right click. So there's probably an easier way to do that. We have done these before, these y equals mx plus b plots. So this is nothing new to us. Okay. So I'm going to choose a linear trend line. And I'm choosing to put my equation on the screen as well as the r squared. I do believe that your ALEKS homework or your lab flow assignment, does require an r squared on there as well, so you will need the r squared. What you don't want to do is set the intercept. You already have a 0, 0 option, okay, so it's already plotting a 0, 0. We don't want to force this line through 0 because that's going to get rid of our b here, our y-intercept. So if I do that, it just gets rid of it. And LabFlow will not accept that. So we don't want to set our intercept to anything. Okay, we want to keep this as a y equals mx plus b plot. Okay, so that then gives me the y equals mx plus b equation that we need for the second part of the lab. So let's jump into the second portion, part 2 of the lab, where we're going to take unknown concentrations but known absorbances, and we are then going to plug those in for our y equals mx plus b. So here, I'm going to try to rewrite this. Y is absorbance and x is concentration. Okay, in part 2, we are going to make new solutions doing the same reaction. Oops. Spelled that wrong. And what we're going to do is take those solutions and we're going to find their absorbance in our colorimeters again. So we'll do a dilution to get the solutions made. We'll then use their absorbances in order to find the equilibrium concentration. So this concentration here, that's referenced as your X value, is going to be the equilibrium concentration of the iron thiocyanate. Okay, so let's jump over into the experimental portion of part 2, show how we make those solutions, and then we'll go into the calculations on how we are going to use this equation in order to help us solve in our ICE tables. So now that we know where those absorbance values are coming from and how we can use those to form our standard curve and to find our y equals mx plus b equation, our second part of our lab has us doing slightly different dilutions in order to adjust where our equilibrium lies. And essentially what we're going to do is use the information about our initial concentrations of our solutions as well as our absorbance to find an equilibrium concentration, and we are going to use that to calculate K for this given reaction of iron mixing with thiocyanate being in equilibrium with iron thiocyanate. So in this part of the lab, we are doing another dilution experimentally. The dilution is in a different table, so we're going to use slightly different numbers for our calculations of our M2s, but we are going to do those in a very similar way, which we'll see in the data workup portion of the lab. So I'm following a slightly different table. I have adjusted my solutions here because the concentrations of the iron nitrate, the sodium thiocyanate have changed. So when you're doing this virtually, or if you're doing it in person, please just make sure you are using the correct concentrations for those solutions and plugging them in properly to your dilution equation, okay? The concentrations from part 1 are different from our concentrations from part 2, so they are different numbers. If you don't use those different numbers, you're not gonna get the right concentrations. It's gonna throw off your entire ICE table and you won't get the correct answer, okay? So make sure you are looking at those different numbers, noting them, putting a little star next to them, whatever you need to do to remind yourself that they are different. So the way we are changing in this dilution is we are now just using 10 milliliters instead of 25 milliliters. So I again have a 10 milliliter volumetric flask, which is smaller than my 25 milliliter volumetric flask that I used in the previous part. For this part of the video, I'm only going to show one test tube, how we make it, how we find the absorbance from it, and when we get into our calculation section, how we can use that to fill in our ICE table and find our K value. What you're going to do after that is then do the remaining test tubes. Obviously, you'll do this test tube with your absorbance that you got from lab flow, but then you can do the remaining ones by yourself because it is really repetitive. Okay, the calculations are the exact same. You just have to change your absorbance value and your concentration numbers, and we'll talk about that when we get into the calculations portion of the lab. So for this dilution, I am using 5 milliliters of a slightly less concentrated iron nitrate, so that's why the solution is no longer orange. Okay, it's now clear because the concentration is lower. Okay, so I'm using 5 milliliters of this. And then I'm going to use 1 milliliter of the of the sodium thiocyanate. So I'm doing test tube number 6 that is listed in your lab flow handout. So I'm doing test tube number 6 as our example for part 2. So there's my solution. Because I'm doing smaller volumes and slightly different concentrations, it's not going to be as dark as my standard curve that we did in the previous part. So just keep that in mind. If you're doing this in person, that they are going to look a little bit different. Okay, but then I'm going to use the nitric acid to fill the rest of the way. Okay. Oh, I forgot a lid. Hold on. Here we go. Put my lid on there, and we are going just mix that up. Okay. So I just took some time off camera just to prepare my solutions. So I put my solution 6 or test tube 6 into this cuvette so that we can read the absorbance. What I also did was I blanked out this solution. Because my iron nitrate solution is now clear, whereas in the first one it was yellow, I do have to create a new blank for this portion. So my blank is now just a clear solution. Because this is so light in color, the absorbance is going to be really small. And obviously it doesn't have any of that yellow color in it. So if I tried to put this in without my other blank, or with my other blank, it wouldn't read any absorbance. So I could put this in here and read the absorbance. Again, it's going to be really small, so 0.03. Now, if we were to go through and make the other test tubes, like let's say test tube number 10, this would be significantly darker and have a significantly higher absorbance. I quickly just went ahead and made solution 10 just so that you could see the difference in the color compared to solution 6. So this one's basically clear, which is now, this one has this kind of peachy color due to the redness that the iron thiocyanate solution has, except now we're just in lower concentrations, which is why it's not as vibrant as our calibration curve. Again, our calibration curve does many different large steps in the concentrations as we saw, so that we could find any of those concentrations given a wide absorbance range. So let's just go ahead and put this into our cuvette so that we can see kind of the absorbance range of our solutions. Obviously your absorbances are going to be different because they're provided to you in LabFlow if you're taking the lab virtually, but we can see here that our absorbance is now 0.12, okay, which is again in that range of our absorbance curve that we saw in part 1, which is why we're able to use it here in part 2. So let's go over to the board and now talk about how we can use this absorption information and our current dilution that we're doing here, along with our previous y equals mx plus b relationship, in order to start filling out those ice tables and starting to calculate K. So for the next part, the calculation portion for part 2, before we can just jump in and start using our y equals mx plus b equation to find our equilibrium concentrations, the first thing that we need to do is we need to fill out our ice table with the information that we know first. Because the equilibrium concentration that comes about from our y equals mx plus b equation is going to be used to fill out our last column of our ice table. But the information that we need in our I and our C rows are still going to be relevant for solving that information. So the first thing that we have to do is calculate our initial concentrations. These initial concentrations are going to be calculated from the dilution that we did in part 2. In part 2 of the lab, we did a slightly different dilution with slightly different volumes. So you need to make sure that when you're calculating this part, you are using the table KEQ2, okay, and using those volumes in order to calculate your concentrations. You'll also see that the concentration of your sodium thiocyanate or your potassium thiocyanate, again, they can be interchangeable, as well as your iron nitrate, those concentrations have now changed. So you cannot use the same concentrations that you did in part 1 for part 2. So you need to make sure that you are using different concentrations. Okay, so for this portion, we're using this to calculate our dilution in order to calculate our concentrations. So let's look at each individual reactant and product. Well, the first one that we can solve for first for our initial concentration is going to be the iron thiocyanate. Obviously, before the reaction started, we had 0 for its concentration. There was no product that was formed. So we're assuming that in order to get to equilibrium, we started with only reactants, and then we went and created our product, okay? So initially, we had a 0 concentration for our iron thiocyanate. That will be the same for every ice table that you're doing. You're gonna end up doing ice tables for test tube number 6, 7, 8, 9, and 10. So that's 5 different ice tables, okay? And they're all gonna be set up the same way. For all of them, the initial concentration of the iron thiocyanate is constant. The other value that is constant is going to be the iron concentration. Because again, in our table where we're doing our dilutions, that volume of iron remained the same. And as we saw in our first part, if it remained the same, it had the same concentration. So what we can do for our initial concentration of the iron, we're going to use M1V1 equals M2V2 for this, okay? However, this is going to remain the same in each ice table. Okay, so the initial concentration of iron is going to remain the same for all of our different ice tables because each test tube had the same concentration of the iron. Okay, so this will be the same for each test tube. Does that mean the equilibrium concentration is going to be the same? No. Okay, it's going to be different, okay, because that's going to depend on the amount of thiocyanate that was present. But the initial concentration is going to remain the same in all 5 ice tables. So we only need to calculate this value once and then put it into all of our ice tables when we are completing this in lab flow. So for my solution here that I had, this in a different color, okay, my M1 for my iron was 2.0 times 10 to the minus 3. Again, your value in lab flow is going to be different, so you can't use this number. You have to use the number that is provided in lab flow, okay? So that was my initial concentration of my iron. My volume of iron that I used in every test tube for that portion was 5 milliliters. As we can see from our table, it's 5 milliliters every time. So it's 5.0 milliliters. Our M2 is what we're solving for, so this M2 is going to be what we put in for our initial concentration for our iron. So this is what we're searching for. And then our V2 is going to be what we diluted it to. And if we look at if we add up all of the volumes of each component that's in each test tube in part 2, that is now 10 milliliters. So that volume is now different from part 1 as well. Part 1 we did 25 milliliters, in part 2 we're doing 10 milliliters. So our final volume here is 10.0 milliliters. Okay, so we have 4 variables, 1 unknown, so we can just solve for M2. So 2.0 times 10 to the minus 3 times 5 milliliters is equal to M2 times 10 milliliters. Again, we don't need to convert our volumes, our volume units, because they're going to end up canceling out when we do our division anyways, so you can leave them in milliliters and you don't have to worry about converting them to liters. So we solve for M2. In this situation, my M2 is 1.0 times 10 to the minus 3 molar. Okay, so that would be the value that I plug in for my initial concentration of iron. So 1.0 times 10 to the minus 3 molar. So if I was plugging this in for my own data, every ice table would start with an iron concentration of 1.0 times 10 to the minus 3, an initial concentration of iron thiocyanate as 0, and now we have to calculate the initial concentration of the thiocyanate ion before the reaction started. Okay, so we're going to do a similar calculation. We're still going to do M1V1 equals M2V2 for that. Okay, so we're doing this again. And the setup is going to be very similar, except if you remember from part 1, our thiocyanate concentration is what varied. So this is the only number that's going to change in the I row of all of our ice tables, because again, in our table from lab flow, the volume of our thiocyanate ion is the one that is changing. So our V1 will constantly change, just like we saw in part 1. So this will vary for each test tube. Okay. okay? So in each ice table, you're going to have a different concentration for the thiocyanate. So okay, so my M1 for this one ended up being 2.0 times 10 to the minus 3. The volume, I'm going to do test tube number 6 as our example for how we're going to fill in this ice table. Okay, test tube number 6 had a volume of the thiocyanate as 1 milliliter. So we can go to our table, look up test tube 6, and it'll say that thiocyanate was 1 milliliter. So that's where I'm getting that number from. M2 is what we're looking for. And the final volume for this test tube, just like in our iron portion, was 10 milliliters. Again, we diluted that to be a total of 10 milliliters in part 2, not 25 milliliters like in part 1. So there is a difference. So this is then 10 milliliters. Okay. So we can now solve. We get 2.0 times 10 to the minus 3 times 1 is equal to M2 times 10. And we can solve for M2, which I don't have on me at the moment. That is 2.0 times 10 to the minus 4 molar. Again, you are going to have a different concentration. Your initial concentration is not going to be exactly 2.0 times 10 to the minus 3. It will be different from the value that you used in part 1. Okay? All of your concentrations when you go into lab flow are highlighted in red. Okay? So just make sure you are looking at the appropriate one for that part. Again, write it on a piece of paper, highlight that it's for part 1 versus part 2 so you are not messing up your calculations that way. Okay? So that gives us an initial concentration of thiocyanate as 2.0 times 10 to the minus 4 molar. Again, this is the only portion of the I row that is going to change in all of your ice tables. This will remain the same, and this will remain the same. This will change. How is it going to change? The only number that changes is the volume of that sodium thiocyanate, SCN, in each test tube. Just like we did in part 1. Okay? The concentration stays the same, the final volume stays the same, the only number that varies is that initial volume. And that's how we get different values for M2. Okay, so you have to keep an eye on that and use the table from your lab flow in order to do that. Okay, so now we have our I row. The other part that's going to remain the same for all of our ice tables is going to be the C row, the change row. How much are each of these concentrations going to change relative to each other? Now, as you may have learned in class, the way that we can get the C row, the change row, is by looking at our balanced chemical reaction. Everything in this reaction is a 1-to-1 ratio. So as iron decreases, the thiocyanate is going to decrease within the same ratio. And because those are decreasing within the same ratio, the iron thiocyanate is going to increase within the same ratio. Okay, so we know that our change row is just going to be minus x plus x. We show that our reactants are decreasing in concentration or being used up by showing the negative sign. So we can say that their initial concentrations are decreasing by some factor. And we can show that the iron thiocyanate concentration is increasing with this positive sign. Since the iron thiocyanate had an initial concentration of 0, okay, we know that the concentration can only increase. If I had a negative here, then my final concentration would be a negative concentration, which it can't be. Okay, so I have to make this portion my plus x because it's increasing in its concentration. We are creating that product, and then we are decreasing these concentrations. We are using them up in order to create that product. So I've made some adjustments to our ice table so that we can now see how we can fill in and solve for E, or our equilibrium concentrations. So in a typical ice table, what we can show is that we can add these down in order to show how our equilibrium concentrations are going to change from our initial concentrations. So for our iron, it would be 1.00 times 10 to the minus 3 minus some value of X, which is going to be our concentration that's changing. For our thiocyanate, it's going to be 2.0 times 10 to the minus 4 minus X. And for the iron thiocyanate, it's just going to be X. Now, as I said before, if we're calculating K, we need to have information not only about the initial concentration, but also about the equilibrium concentration, so that we can easily solve for X and get an equilibrium concentration for each of these values or each of these reactants and products that we can then plug in to our K equation, okay, to the equation we saw before. Okay, so how do we solve for X? Well, that's where our y equals mx plus b equation comes in. Remember, y was the absorption or the absorbance of whatever our solution was, and x was our concentration. X is the concentration that we need to find here as well. So what we can do for each of the test tubes that we looked at in part 2, I only showed you one. I have a second one in case we need to show the calculation again. But you have 5 that you're going to do, okay? So here we're gonna do test tube number 6 first with my numbers, okay? We can use the absorbance that we got for that solution in order to solve for this X, because that X is showing us the equilibrium concentration of our iron thiocyanate. If we know this X, well then we can plug it into these two reactions, or the equations I should say, and solve for our equilibrium concentration that way, okay? So let's take a look at that. We had our y equals mx plus b equation set as y is equal to 1935.7x minus 0.0086. Remember that y is our absorbance value that we got experimentally, that was given to you in LabFlow if you're doing it virtually. And X is going to be the equilibrium concentration of iron thiocyanate. Okay. So, all we have to do for each test tube is plug in our absorbance as Y and solve for X. So, I have my absorbance for test tube number 6. My absorbance was 0.03. So 0.03 is equal to 1935.7x minus 0.0086. That's an 8. Okay, let me grab my calculator so that we can solve this together. Okay, so I'm going to take this 0.03 and I'm going to add to it the 0.0086, so plus 0.0086. Okay, so that gives me 0.0386 is equal to 1935.7x. Then to solve for x, I'm just going to take that 0.0386 and divide it by the 1935. So divide that number by 1935.7. And I get a concentration of 1.99 times 10 to the minus 5 molar. Okay, so that's my value of x here. So we can plug that in for x. I'm just going to show it in the same box, but in a different color. So x is now 1.99 times 10 to the minus 5 molar. Now that this is our x value, I can plug this in to solve for x here. So I'm going to take that 2.00 times 10 to the minus 4 and subtract off 1.99 times 10 to the minus 5. So let's do that. 2.00 times 10 to the minus 4 minus 1.99 times 10 to the minus 5. And I get an equilibrium concentration for my thiocyanate as 1.80 times 10 to the minus 4 molar. And we can do the same thing for the iron. We can do 1.00 times 10 to the minus 3 and subtract off 1.99 times 10 to the minus 5. And I get 9.80 times 10 to the minus 4 molar. Okay, so those will be the values that you end up plugging in for your own ice table, I believe is how you're doing it in LabFlow. Just follow what LabFlow says for you to do for those tables, whether it wants you to have this in X or not in X. But you will end up solving for all of these concentrations as well. Okay, so that's how we solve for those equilibrium concentrations. Now, just because we have the equilibrium concentrations does not mean that we are done with this portion of the problem. Okay, once you have these equilibrium concentrations, we now have to do the goal of our of this portion of the lab, and that is going to be determining K. So we know, I'm just going to quickly erase my subtraction here to show how I got my concentration there. Okay, just need the extra room. So we know that K is equal to the concentration of iron thiocyanate at equilibrium divided by the concentration of iron at equilibrium and the concentration of the thiocyanate at equilibrium. So our ice table allowed us to find those three values, 1, 2, 3 concentrations. So now all we have to do is plug them in. So I know that K EQ, or K at equilibrium, also referred to as Kc, they are the same thing, okay, is the iron thiocyanate concentration, 1.99 times 10 to the minus 5 molar, divided by my two concentrations of my reactants multiplied together. So my iron concentration is 9.80 times 10 to the minus 4 times 1.80 times 10 to the minus 4. So we can plug that into our calculators. So I'm going to do 1.99 times 10 to the minus 5 divided by 9.80 times 10 to the minus 4 times 1.80 times 10 to the minus 4. Make sure when you're plugging this into your calculator that you're using parentheses appropriately. So I will make sure to put like extra parentheses around the denominator to make sure that your calculator knows to multiply those two values together and then do the division. So just keep that in mind. And I get a K that is equal to 112.8. I'm not being specific with my significant figures here, so you're just going to have to track your numbers in LabFlow to show proper significant figures, so just keep that in mind. But I get a KEQ of approximately 112.8. Now K is unitless, so there's no units on there, so you just leave it as is. So this is for test tube number 6. Okay, you are then going to plug in the information for test tube number 7, 8, 9, and 10. Okay, so we know that as we change our test tubes, the only number that's going to change in our I row is going to be the SCN concentration because we varied that volume in the test tube. Okay, our change row is going to be the same for every ice table. The iron concentration initially is going to be the same for every ice table, and the initial concentration of the iron thiocyanate is also going to be the same with every ice table. When we differ, when I go to solve for my X here, The only thing that's changing in our y equals mx plus b equation is going to be the absorbance. So this will change with each test tube. So that'll be each test tube's absorbance from that portion. So instead of 0.03 for test tube number 6, I think for test tube number 10 and what I did previously, I got 0.11. So I could, instead of putting 0.03, I could write in 0.11 and solve differently and get a different x, and then that would change how these variables change as well, okay? But what we're gonna find is our KEQ is going to come out to be approximately the same every time, because as we know from our knowledge of equilibrium from our past few labs, K is only going to change if the temperature is changed. We didn't do anything with temperature here. So now that I'm varying the concentrations, as one gets larger, another one is going to end up getting smaller, and they're going to balance each other out, and that's why K is going to remain constant, or generally constant, okay? It's not going to be perfect, okay? But generally constant throughout the entire ICE tables that you're going to do. So once you get all 5 of your KEQs, you're going to add them up, you're going to divide by 5, and you're going to get an average K value, and that's going to be the end of the lab.